Yeah,
Wonderful. Great
please.
stuff. So first, I want to give a very, very brief summary of the rhythmicity of the brain. So as you all know, there's a firing of neural ensembles that organize in a very emergent manner to fire in synchrony. And traditionally, we've grouped these rhythmicities in distinct frequency bands when doing EEG of someone's brain activity. So you have very slow activity in the delta range between 1 to 4 hertz, and then also quite fast activity above 25 hertz. But one of the first distinct frequency patterns that was identified was in the range between 8 and 12 hertz, the so-called alpha range, which is most pronounced when you close your eyes and then you have an electrode measuring your electrical activity at the back of your head, so aligned with the visual cortex as well. And that rhythmicity is very easy to measure. It's such a distinct and prominent peak in the frequency profile that even if you just look at a live readout of someone's EEG signal as they're being monitored, you can kind of see it with the naked eye, even. There's a very distinct oscillatory rhythm to it. And once you perform decomposition of the frequency profile and you isolate the alpha spectrum between 8 to 12 hertz, for every person you will find a peak which is especially prominent. So I would say for most people it's around 10 hertz, but there's some variation between people. And I'm quite specific about this because it'll be more important later on in this talk. So this alpha frequency band is easy to measure, easy to recognize, very prominent in people. And as we'll see, there's also quite a bit of talk about its potential um, consequence or impact on cognitive capabilities. So, for example, there have been quite a few researchers who found a, a connection between pathological alpha activity, so alpha, which is not falling within the norm in terms of its frequency profile, and a couple of neuropathologies. So with ADHD, for example, many researchers have found a slower individual alpha frequency, and that then correlating with attentional deficits. With PTSD, there's lower power, so like a lower amplitude, and also a higher frequency individual alpha that correlates with this cortical hyperarousal. With depression, like generally lowered alpha activity across the board, and with Alzheimer's, then like reduced individual alpha frequency power, which would then correlate with impacted memory functioning. Um, at this point, though, I do want to say that this is not monocausal, so it's not that if you were to correct the alpha activity, all of the associated symptoms of these neuropathologies would go away. With that said, though, it is an interesting piece of the puzzle. So, from my point of view, and this will also be one of the core thrusts of this presentation, there is some hope that we could leverage some of the insights I'm going to talk about to hopefully at least alleviate some of the more severe negative symptoms of said neuropathologies. Um, because there is a good case to be made that even though alpha in itself would not be something which would alleviate all the problems, it has a modulatory role to play in cognitive processes, mostly around neural inhibition, that would then impact sad neuropathologies that I listed on this slide. So I want to give a brief summary of another field that also relates very much to what I'm going to talk about, just neurofeedback. A few of you might be aware of that paradigm already, but just to briefly summarize it, when I just talked about pathological alpha activity, I also implied, of course, that there might be something to be gained from correcting said alpha activity to be again in the, in quotation marks, normal or healthy spectrum, which you would find with most people around the world. They fall into a certain EEG pattern of activity, which doesn't deviate strongly. And one way to correct that alpha activity traditionally would be an approach called neurofeedback. And it works in the following way. You have a participant or a patient who are wired up to an EEG to monitor the brain activity in real time. This brain activity is then processed. So, for example, we would find the delta, the deviation between the participant's current alpha activity and the desired goal state that we would want the alpha activity to be in. And we give the participant or patient some kind of visual representation of how big that gap is. So, for example, you could imagine a blue square on the screen that turns a starker, brighter, more intense blue as the participant or patient gets closer to closing the gap between their current alpha activity, which is pathological, and the alpha activity that they want to be in. And there have been quite a few studies which have shown that such training has Hebbian effects. So it affects the plasticity beyond just the training itself, but it has long-lasting effects. But that's really only part of the equation. The other one that I want to talk about is that there were also some findings that have demonstrated homeostatic effects. Um, so there is one study I found very interesting by Klitsch and colleagues, where they had patients with PTSD, and they gave them neurofeedback training, which was meant to further reduce their alpha amplitude. So if you remember from the previous slide, I said that for PTSD patients, you already have reduced alpha activity compared to healthy populations. And with this neurofeedback training, what they then found was not a Hebbian mechanism, where you would have decreased alpha activity even further, but rather it increased the alpha levels post-training, as if you had a gummy band and you would pull it further and further away from its initial position up until it snaps and then regains its original baseline position. Um, so there is also something here which is very interesting, namely that there seems to be a corrective mechanism in the brain, some kind of homeostatic principle, which might ensure a greater degree of stability, so preventing extreme oscillations in either direction. All right, so this kind of sets the baseline for the talk. What I now want to talk about is photic stimulation. So with neurofeedback, it's great that this already exists as a paradigm, but it does require quite a bit of initial training of the participant to gain the necessary skill set to understand how to self-regulate their own brain activity in response to the audio-visual representation of the brain activity on screen or over speakers. So there's still good value in focusing on how we could perhaps shortcut this through direct brain stimulation. And there are, of course, quite a few invasive paradigms, but my own research was focused on non-invasive brain stimulation, and particularly rhythmic photic stimulation. Rhythmic because it then allows for us to capture the neural response via entrainment, and photic because it is a very powerful, non-invasive, and just minimally uncomfortable way of stimulating the brain. What you see here is a photic stimulation machine from the 60s. It has been around for quite a while, but the one that I used was the Lucia light stimulation machine. Here it's a very bright lamp at over 6,000 lumens. I think it's close to 7,000. And it allows for quite precise control of the individual flashes. And we'll talk about this in a bit more detail later on in the talk. But the participant would sit in front of it with their eyes closed, and then the lamp would start flashing at them very bright lights. And through the flashes, we would entice a certain neural response. So one very well-known experiment is using fixed stimulation at about 10 hertz in order to entrain the alpha rhythm. And what has been found in the past is that, generally speaking, as you do this, you would boost alpha activity as the internal neural oscillators being entrained. And I wanted to understand this a bit better, but what I found did surprise me. So what you can see here, just to kind of make it a bit clearer, is a trace of the internal neural oscillator in the black line, and the red line is a photodiode measurement, which shows where the flashes were set in relation to the endogenous oscillator, the neural oscillator. The little white bulbs that I've put on the slide here, like those are essentially, that's the flash of the lamp, and the little black bulb is no flash, so it's dark. And this would be fixed stimulation at about 10 hertz. So what I found here was at this 10 hertz stimulation frequency was that, yeah, you did see a response during stimulation, but the post-stimulation window was really surprising to me. So in the pre-stimulation window, this would be the brain activity of the participant before any kind of photic stimulation is applied. Then in the middle row, you see stimulation at 30, 60, 120 seconds with the brain response to the flicker as it's happening, to the 10 hertz stimulation. But the post-stimulation window shows across the entire brain this strong decrease in activity. We found that this was quite long-lasting as well. I'll talk about this a bit more on a subsequent slide. But first, I wanted to kind of show it in motion. So you see the alpha activity during this 60 seconds interval of 10 hertz photic stimulation with the pre-stimulation window on the top left. Then the top right shows the immediate period after flicker offset, so immediately after the stimulation ends. And then the broader post-stimulation window where stimulation has already gone away for a little bit, but the brain still shows this overall suppression effect. And it's really striking to me how sudden this post-stimulation suppression is. It's like you're putting a weight on a system and then you take it away, like this immediate kind of relief response. It's very interesting because it's so imminent. Here, this slide has many data points. I apologize for this. I kind of want to speed through this a bit. The core takeaways really are that the post-stimulation suppression in the alpha range is strongly significant across the entire cortex. So both occipital areas, which is where it's most pronounced. It's also where, of course, the visual cortex sits. So this is what you would expect. Like if you use a stimulation modality which is visual, you would expect the impact would be strongest in the visual cortical areas. And then it's still present though in the medial and frontal areas as well. And the stimulation length here has a certain degree of impact in terms of how severe this post-stimulation suppression is, but it is present even for the shortest amount of 10 hertz photic stimulation. So it's a very consistent result. Looking at a single trace here, where you can see the stimulation effects and the post-stimulation suppression over time, you can see that immediately after stimulation ends, which is the area shaded in blue in the figure in the middle, that shows the stimulation time period, it immediately drops. And then even though the alpha power rebounds a little bit, it does not fully recover to its original baseline value. So the red line in the middle would be the average alpha power in the pre-stimulation period, and the green line would be the average power in the post-stimulation period. But yeah, the most telling thing here again is just that it's across the entire cortex. And we didn't find a clear rebound to the original alpha power. And since then, other researchers who have picked up on my research and have built on top of it have tried to find more information on when this rebound happens. So when does alpha power regain its original pre-stimulation window? But this is still an open question, because even for a couple of minutes after stimulation has ceased, it has still not happened. So, however, there are things I'm going to talk about which have led to this wiping out of the alpha power suppression after stimulation. I might actually glance over the slide. This just shows the coherence values between the um, OZ electrode and the photodiode. So this is just a case in point that the entrainment is almost imminent. I guess that's the only thing I'll say about this slide. So as the photic stimulation starts, almost immediately, it takes like 1 to 2 cycles, you'll find that the activity of the neural oscillator as measured over the OZ electrode has really high coherence with with the photodiode. So it takes on average about a second to reach mean coherence. So it's quite quick. The brain just very quickly adopts to the rhythmicity presented in the photic stimulation. I wanted to say one thing, though, about the duration and the intensity of suppression based on different lengths of stimulation. So on the left-hand side here, you can see the post-stimulation window following 60 seconds of stimulation. And on the right-hand side, it's for 120 seconds of stimulation, where areas that are statistically significant in suppression are highlighted with white outlines. So you can see that it's a little bit more sparse for the 60 seconds of stimulation condition, whereas for the 120 seconds of stimulation, it's longer lived and it's much more consistent throughout. This is another very interesting area, though, because we've talked about how like length of stimulation might have a bit of an impact. There's other researchers who have looked into whether the brightness of the lamp also has an impact, and it does, although I think this research is still ongoing. Another thing that does have an impact on the response to stimulation is delta between the individual alpha frequency and the stimulation frequency. And what I found very interesting is that this relationship is not straightforward. So on the left-hand side, you can see the during stimulation and post-stimulation response to photic stimulation at 10 hertz, which is the like fixed stimulation frequency. The red bars on the left-hand side, they show the degree of alpha power change, like the cumulative effect size during stimulation. And you can see that as you get closer to there not being much of a difference between the individual alpha frequency and the stimulation frequency, suddenly during stimulation, the effect size sometimes like even like dips negative, as if when the photic stimulation gets more effective, that kind of homeostatic counterbalancing kicks in more readily. So the greatest positive effect size on alpha power enhancement during stimulation, we actually found when we had a stimulation frequency which was overshooting the individual alpha frequency by about 2 hertz. Whereas for the suppression, you can find a much more clear-cut story where as you were approaching a point of there being no divergence at all between individual alpha frequency and the stimulation frequency applied, there you have the strongest post-stimulation alpha power suppression. And I think this also gives some additional credence to the idea that the lack of a strong positive response during stimulation as a strong alpha power enhancement when there was next to no difference between individual stimulation frequency and the individual alpha frequency was because it led to a kicking in of the correcting principle via homeostatic mechanisms. But there is something that I found that does completely eradicate this alpha power suppression. An obvious one, of course, is you can open your eyes or you can engage with other stimuli. But in one experiment here, we gave people stimulation at 10 hertz and stimulation at 3 hertz. And we gave them a task to fulfill. So the task was a reaction time task where they had to press a button when a visual flash was presented to them with their eyes closed. So in practice, this looked as follows. We had a participant placed in front of the light stimulation machine. They had their eyes closed. The stimulation started. And then after the stimulation ceased, they were informed with an audio cue if they now had to, as quickly as possible, press a button when they see the next single flash, or if they could safely ignore it. If they were told that they had to pay attention, because this is a reaction time test, this is the figures you see on the left-hand side here, the RT test column. What you can see is that immediately around the time that the flash was presented, that they had to respond to a button press, the alpha power suppression just went away entirely. Whereas if we told them with an audio cue that the next flash that they see, they could safely ignore, they wouldn't have to respond to it. Even though there is also immediately after that flash is presented to the participants, falling away of that alpha power suppression, it just comes back. So it seems like the willful engagement with a task where there's a deliberate focusing of their attention on something they need to do, eliminates the effect of the exogenous stimulation from before. So that is interesting to see, that just engaging willfully can override such intense stimulation. But if the participant is not asked to perform a reaction time task, but rather we just apply a TMS pulse and we check for whether the TMS evoked potential in any way differs in a period of post-stimulation alpha power suppression. There we do find a difference. And this is because, as I mentioned at an earlier slide, there is a quite credible link that has been established between alpha power and neural inhibition. And if we decrease alpha power and consequently the potential for it to successfully inhibit neural responses, we would find a greater evoked potential after transcranial magnetic stimulation. And to make sure that this is due to the effects of the 10 hertz stimulation, we stimulated at both 10 hertz and in the control condition at 3 hertz. And in the post-stimulation time period, where alpha power was suppressed, we then started stimulating over the occipital area and measuring the response. And we saw that both in frontal, medial, and occipital areas in the experimental condition, we saw significant differences in immediate response to the TMS pulse. So as long as the participant doesn't willfully engage with some other stimulus and kick into action in terms of them actually being agents in the world, and we just let the brain be as is after stimulation, then we can leverage this for a different kind of impact of a single TMS pulse. So here so far, I talked about traditional stimulation, and I want to briefly talk about phase-dependent stimulation as well. So with fixed stimulation, as I said, individual flashes would follow a static predefined sequence So 10 hertz across the board, for example, as we did in the previous experiment I talked about. But there's also the opportunity to do phase-dependent stimulation. So placing flashes in alignment with, for example, troughs or peaks in the signal. So what we did here is we performed something that we refer to as a phase shift. So first we entrained the neural oscillator through fixed stimulation, and then we incorporated one additional off period in order to place the next flash in alignment roughly with the trough of the oscillation. Or we introduced another peak stimulation element by having a phase shift with an additional on signal. I'm going to talk about this on the next slide, but for now, on the trough stimulation element, what you can see is that as the trough stimulation hits, you find a slowing down of the response with an increased amplitude. It's a little bit like perhaps standing behind someone on a swing and waiting till they come very close to you and giving them a push so that next time they go higher, but the total speed of that oscillation has slowed down as well. And with peak stimulation, you find the opposite. So imagine that now you're standing not behind a person on a swing and you push them, but rather you stand in front of them. So at the top of their swinging motion, when they're closest to you, you push them back. And that increases the speed of the oscillation whilst also diminishing the amplitude of it. So they don't go as high the next time. And this is what we found here. It also affects the coherence measurements quite a bit. So for the trough stimulation and peak stimulation, you do find, of course, this immediate drop in coherence between the electret OZ that we measured from here and the photodiode that we used to monitor the precise flash sequence that I talked about in the previous slides. So you find this expected drop in coherence immediately after we present a phase shift through either peak stimulation or trough stimulation. But there's also a difference in the frequency response besides that, of course. So, for example, with the trough stimulation, you find greater coherence activity in like lower frequencies. And this is something we explored a bit further in a follow-up experiment where we made the entire stimulation signal dependent on what was happening in the live neural signals. So every single flash was driven by neural signals. Specifically, we had two conditions. One we refer to as negative feedback, which is roughly aligned with the trough stimulation condition, and one was positive feedback, which is roughly aligned with the peak stimulation condition. The idea being that for negative feedback, we would have a dynamic threshold where if the signal would fall below it, we would then trigger a flash. And for positive feedback, the opposite was true. When a threshold, a dynamic one, was crossed, surpassed, it would then trigger a flash. And the response here is very similar to what I talked about before with the phase-dependent stimulation, where for the negative feedback, just like with the trough stimulation, you could find more lower frequency coherence. Here, the signal, the stimulation signal, which is what you can see on this slide, is moving further downwards. So you have lower frequency activity. The peak there is at about 7 hertz compared to the positive feedback condition where the peak is close to 10. So you do find a bit of a corrective mechanism here as well. And at this point, I'll just sum it up real quick to really give you the gist of it. Because my core point that I want to get across is that with rhythmic photic stimulation, whether it's fixed or phase sensitive, you can quite quickly entrain those neural oscillators in your target frequency range. It only takes a few cycles. At 10 hertz specifically, you can boost alpha activities primarily in occipital areas, but there is a point at which you reach an overexcitement, and then this results in long-lasting alpha power suppression. There's a possibility for you or anybody to counteract this through willful behavior, such as paying attention, or by introducing some other stimulus that's captures attention. But in absence of that, as I showed you in the TMS experiment, it does affect the way that we can impact the brain in other ways. These stimulation effects are phase sensitive, so you get a diminished response if you hit at a peak in an oscillatory cycle, and you get a heightened response if you hit at a trough. And all of this really can be leveraged to correct or at least diminish abnormalities in frequency profiles of neuropathologies. And my hope is that this would then diminish some negative symptoms experienced by people who suffer of these conditions. But yeah, thank you very much, both to you and to all the people who made my research possible all those years ago. Of course, my supervisors, Christopher Buckley and David Schwartzman, Anna Seth, and then also help from friends and assistants who helped me in setting up experiments and collecting data. And also to you for listening. I very much appreciate your interest.
Hey, thank you so much. Great talk. So we really take a short break, 5 minutes. After that, we go to the discussion part.
Yeah.
So yeah, thank you for talk. So now we take a short break from restarting from the 8 6:40. I mean uh yeah, JST.
Mhm.
So